It's preparing to live stream.
All right, here we go. It looks like it's recording. So, Vivek, if you want to introduce the Bionics meeting, and you can pin Eric afterwards to get him set up for the presentation. And thanks everybody for coming today. It looks like it's recording.
Okay.
So, Vivek, and Vivek, you'll have to mute your YouTube in the background. Pin Eric afterwards to get him set up. This happens to me every time. I set the recording and then it starts playing. There we go.
It's propagation delay there, buddy.
So while Vivek is getting set up, again, we do these meetings once a month. This is the Bionics meeting. We also have a series of other meetings, including chapter leaders and for new members. But specifically, this meeting is going to be looking at new advances in Bionics, some particular projects and community members that are working with Bionics. We're lucky to have Eric Bubar today with us, who's going to share some of his recent research and how it interconnects with the curriculum and the new program that he's running at Marymount University. And again, these community events are supported and managed by Vivek, who has been also working in the background on the hub space. So I'll add a link to that space. And this is a place where dialogue can continue and people can post their research and questions in between the meetings. So Vivek, if you want to unmute yourself. You can pass the maybe pinned screen to Eric. I can't do that, but
can we enable screen sharing as well?
Yep. So if you make Eric a co-host.
I'm a professor. Of course, I've got a PowerPoint.
So Vivek, if you click on the three little dots next to Eric's name, you should be able to make him a co-host. And we can't hear you, Vivek. You're on mute. If you click on the three little dots next to Eric's name,
he's co-host.
You should be able to make him a co-host.
Eric is co-host.
Perfect. Got it. You should be able to see my screen now.
If you click on the Vivek, you'll have to X out of, you mute yourself and X out of the YouTube video that's playing in the background. That's the recording.
Got it. You should be able to see my screen now.
Okay.
Got a bit of an audio loop. That happens to me all the time. Cool.
And everybody can see, you can see the screen. Perfect. Okay, so thank you for inviting me to come and talk. So what I put together is just a couple of slides about what we've done and what we're doing based on what we learned from what we've done. I do want to recognize the two students that have mainly done a lot of this. Megan Gagnon, she gave a talk, I believe around March this year for the Bionics group. She's now a prosthetist in Seattle. And then Catherine Sanchez did a lot of VR work with figuring out how to do VR training for 3D printed prosthetics. So they had a lot of hands in this. So I am the head of a new department of engineering. It starts in the fall. We were supposed to have 2 students and now we've got 11. So we're off to a good start, I think. So past work that we've done, we tried to start doing some grip testing way back in like 2014. I think that's back when there was the e-NABLE Community Foundation and lots of people that are no longer around. So what we did there is we used something called Theraputty, which is used by occupational therapists to kind of quantify people's grip and how strong they can grip stuff. This was actually pretty good for the hands. Because you can do multiple kind of stiffnesses of this putty. So this would give you a good idea of how well hands would grip. We also did some basic grip strength testing with a blood pressure cuff. So this is how grip testing is done if you are not strong enough to squeeze a dynamometer, which is what we would normally do. They use this in stroke patients. So our e-NABLE hands are about as strong as a stroke patient's grip. So what you do is you wrap up a blood pressure cuff slightly inflated, and then you just squeeze it with the hand. So we had an input force that we'd measure with just a force spring scale, and then the output force that we'd measure in millimeters of mercury. This is a very maker-friendly test. And what we did with that is we found every single e-NABLE hand at the time, they were all the same. There was no difference in any of them. So really, friction in the fingertips, that was more important for grip strength. And basically, you choose the design that you like the looks of the best. Functions didn't really matter. So we'll come back to testing more in just a moment. So the other stuff we've done, we have done some electronic prosthetics. So I can show you an example.
Hi, what's your name?
I'm Megan. I'm in Maynard University.
Yeah.
And
What lab do you work in?
the physical science physics lab.
The physics lab. Only physics. We only do physics, no physical science. Okay. And what do you have?
I have my myoelectric hand that I made my summer research with Professor Bubar. And what it does is it takes EMG signals from my arm and then sends it to my little chip right here, which talks to the Arduino, which has the code information on what hand motion I want to do about pose. So if I make a fist, the hand also makes this.
Okay.
If I release, my resting pose is just relaxed. If I wave in, hand does the hang 10 symbol. If I spread my fingers, that's a piece.
Okay.
And then wave out, just if it's glitched, it relaxes it to this as well.
Okay.
The next pose I'm going to do is if I double tap, it'll be a point, but I haven't put that in yet.
Okay. Whose hand design is this originally?
So this is Open Bionics hand right here that holds the motors and everything in there, and it actually says it on the top. But then I did the arm and then all the casing in there as well.
Okay. And you did the coding for the Arduino?
Correct.
And that was based on some other work. Whose work was that based on?
That was from the actual armband. It was
The Myo armband.
the Myothematic armband. The code was on there, and I kind of used the framework on that code, which was for a different Arduino board and different motors, and I kind of used that to guide me on how I wanted it to work with my hand and my circuit.
Okay, so you got some information about what the nicest kind of multi-pose prosthetic we made. The 3D printed pieces, lower palm was NinjaFlex, upper palm was PLA, arm was PLA. The lower palm and upper palm were both Open Bionics Ada hand design, and the arm portion was actually PLA. We just designed and printed that in-house. All the electronics are about $500. The Myo armband was from Thalmic Labs. We used an Arduino Uno, Onyx linear actuators, an HM11 Bluetooth chip, flashed with some custom firmware, wiring based on instructions from Po Paraguay, their Myo arm, their first design, and then modified that code. So what we needed to do was kind of do some further work on the design. If you look at this kind of mess of circuitry, this is not something that a regular everyday kind of maker is going to be able to make. Our typical e-NABLE volunteer isn't going to be able to create this. This is a little bit too advanced for that kind of maker. So what we wanted to do was try to simplify this. So where have we gotten to in simplifying it? So what we want to do, we're using the same lower and upper palm. We have a slightly nicer arm now. Instead of the Myo armband, because that has been discontinued, you actually can't buy that anymore. We're now using a force-sensitive resistor. So that's this little guy. You can squeeze this, and the signal that you get out depends on how strong you squeeze it. So I think this is probably, I think I saw Lawrence on here. I think he's using that in his design. And this is something that there's an Italian maker, I think, who took the kinetic hand and made that Bionic, and he's using this little guy as well. Okay, so we have that for the muscle sensing. What you need to do is you really need to mount that very well on the arm in a good place where when you flex, it'll actually apply pressure to that and you'll detect the signal. So that's instead of having to do myoelectric detections. Myoelectric detections, my opinion, probably more trouble than they're worth if you want to make a design that lots of people can use. You have to do filtering, you have to filter out noise, you have to filter out motion that causes signal artifacts. That's probably just more complicated than what we would want to do for our particular work. We are not using an Uno anymore. We've shrunk it down. We're using a Nano 33 BLE so we can have Bluetooth. So you don't need to do a lot of complex coding and circuitry to get Bluetooth working. It works out of the box with the Nano. And the Nano is quite small. We're using Onyx linear actuators. This is the one place we haven't cheaped out. We want to use these because they work well. They're reliable. Well, they were reliable for a couple of years, and they're pretty strong for the price. To control the motors, instead of having to do lots of soldering, lots of complex kind of wiring that might be difficult, we use a pulse width modulation servo motor driver board. So that lets you plug in all the servos that you want, up to 16 of them into just one little control board. You can run the power straight through to that control board. Very simple, very easy to code. So it simplifies the process a good bit. For power, we're using two 18650 lithium poly batteries. That provides about 7 volts. So that's plenty to control the motors and to power the Arduino. Nice thing about that is those batteries are commonly available all over the world. They're the same batteries that they use in electronic cigarettes. So people can get these pretty much anywhere. Not as easy to get in the US, but easy to get overseas if you go to the right place. The Arduino code we're using, it's nothing custom, nothing fancy, no flashing of firmware or flashing complex codes. The kinetic Bionic hand, he's got you using a different kind of M5 kind of Arduino board, and it's not super well documented, so it's a little tough to figure out. You don't have to do any of that. Everything that we create, we're trying to use with just Arduino and just kind of basic Arduino examples. And you don't need any of the Bluetooth chips, any of the complicated wiring. And what we're trying to do now is we're trying to make a hand that just opens and closes. We're using an open source Bluetooth app to control any kind of multi-purpose use. And what we really need is a proper battery circuit to make charging a bit easier than it is right now. And as Ben said in the chat, yeah, feel free if you got any questions, post questions anytime. So why did we make the decisions that we did? We're not going to do myosensing. It's just tough. The myosensors that we have, and we do have some decent myosensors. So we have, this is the one that I would recommend people use if you're going to use one. It's got non-sticky contact electrodes to read the actual muscle signal. The cord is pretty good. It filters out a lot of the electrical noise from movement. The problem I run into with it, I have a lot of students kind of try to recreate the projects that I make. And when my students can't do it, that tells me that there's a cutoff between what somebody can and can't do. So if my students can't figure this out or can't get this working reliably, then somebody in another country that's trying to use this, they're probably not going to be able to either. So I'm trying to cut that out. Right? This would be nice, and we could do this for kind of research purposes, but for larger scale use, I don't think this is appropriate. So that's why we move on to these little guys. These little guys, super cheap and super easy to code. There is a little bit of soldering involved in getting a resistor on the end of this to get the signal out that you want. But again, not too difficult. We're using the Nano 33 BLE because it's small size, lots of pins, onboard Bluetooth, low cost. It's about $20 and easy to program. And there's tons of support out there online for it. You can find better boards. You could use Adafruit Trinket. You can use the M5 one that this Italian guy's using, but those aren't as widely available and they're not as well documented. I give it to students, and when the students can't find the code, that cuts it out for me. So my students can find the Arduino Nano 33 BLE, super easy. The Onyx motors, these I don't skimp out on. I think if you want a multi-pose device, you want to use those. Those are relatively lowish cost. They're about $70 a piece. So it is expensive, but they work reliably. It's what Open Bionics is using, and I trust Open Bionics to know what they're doing. The problem with those that we've found just recently, actually just this week, a student was playing with it and ripped some of the little ribbon cables that were in it. So I can't show you the hand. It's been working fine for 2 years. 2 years. I'll stick it in a closet somewhere and bring it out. And it works perfectly. Works great with the app. And then a student breaks it right before I'm going to present it. So that not ideal for presenting to you, but it does show us that there's some design things that we need to do. We need to take that into account. So maybe those aren't the perfect linear actuators. The motor driver board, this just simplifies wiring a lot. You can plug all your wires into this board and all your servo wires into a board instead of having to run a bunch of wires and do a complex breadboarding kind of circuitry. The 18650 batteries, I mentioned this is plenty of voltage, 7.2 volts to run everything. It's a little bit bulky. I'd like to bring that size down. And again, charging the circuits, I'd like a more intuitive way to do this. There's a bit of a trade-off right now, the way the designs we do, you kind of have to take the batteries out and put them into another charger. That's inconvenient because it's not simple to charge, right? You can't just plug in the arm, but it is convenient because you can just have 4 batteries. So you can take out your 2 batteries, put those into charge, and then put 2 charged batteries in. So you're cycling out the batteries. So there's a little bit of trade-off for convenience, but it's kind of nice because you can power it that way. Also working on trying to make sure that there's an alternative power source so that you could power it with just 4 AA's. The reason I like doing this is I follow a lot of people on YouTube that talk about their bionic limbs. That's how I get my user experience. I figure out what are their problems. And I see the constant complaint, I forgot my charger. My electricity's out and I can't charge it. I can't plug it in. And they're all proprietary. So if we want something that can be widely used, we want a power source that can work for lots of people. So 18650, you run out of batteries, go to the e-cigarette store and buy a couple new ones. If you can't find those, then go find some AA's and run your arm off of AA's. So I think that makes it a little bit easier. Again, thinking about balancing complexity with simplicity. And then the basic Arduino code. Again, this is all stuff that we've built off of simple example code that you can find in Arduino libraries. So none of the stuff I'm doing is really, really super complicated. The things we want to do. So I look at literature sources, discussions with prosthetists, orthotists, lots of people on LinkedIn making connections with prosthetists that are actually using 3D printing now. I'm starting to see that emerge. They're not hiding from it. They're actually saying, this is good, this is useful, we want to use this. I'm getting them to serve on advisory boards for the engineering program. Talking to users, looking at YouTube videos from users, e-NABLE discussions. Vivek posted a great complete guide to bionic arms and hands. That website is a useful, great resource to learn about these things. What I found is, and the literature backs this up, and that bionic guide backs this up, multi-articulating hands, they're overly complex and people aren't using the functions. Hey, this hand does 27 different poses and the people actually use 2 of them. It's some words on a spec sheet and it's not actually useful. Individual finger control isn't appropriate for an ultra low cost bionic device. Somebody doesn't need to be able to do this, right? If they want to do this, they're going to do it with the anatomical hand that they potentially have. And anything that you make that does this isn't going to create the function that they are going to actually want. So don't lie to them. Don't try to convince them that you can do that, because it's not going to happen for really, really low cost at this point. So what you want to do is focus on these low cost multi-pose bionics. I think they're great for learning, great for development, great for people to play around with, but they require a lot of extra skills. So what do you want to do with the bionic design? I think you want to kind of focus on just a couple grips. And these are the power grips that people most often use. So a cylindrical grip, spherical grip, hook grip, lateral comprehension, and pinch grip. These are the kinds of poses that people want to do with their prosthetic hand. And how often do they actually grip things? What are they using hands for? They're a lot of times using it not even to grab something and hold something. They're using it as a hook, something that they can just loop something over. So you need to kind of design your device to what people want to use it for. So our approach to multi-motor bionics now, we're using the Open Bionics Ada hand. One of the problems we've identified with some of the hands is the stringing isn't quite as reliable for reliable movement. They do stretch a little bit, and sometimes they'll snap, or things will come untied. So we're also looking at linkage-based kind of solutions. I'm actually studying some Disney World patents on animatronics and trying to learn from their animatronic departments about what they do to try to get some of those into simplified electronics. Using an FSR system with MIT App Inventor, we wrote a custom app for multi-pose function. It worked for, again, 2 years until we had a problem with the ribbon cable this summer. We need a better battery system and a AA system. And we're implementing now, for demonstration purposes, a button system, so you can just push a couple buttons to control individual fingers, and a potentiometer, to a little dial to control the hand. So this is the system that we have. So this is the Nano. This is the motor driver board. This is a potential charging solution for AA batteries. Here's the AA's that we have it running off of. You can see the problem with the stringing system. The middle finger didn't tie down quite so well. So in the video, it looks like we're flipping people off. We want to be careful with that. But here we can show you, let's
printed
forward a little bit.
Part hard plate.
Yeah, these are all just the pieces.
The electronic
system.
Power source. That
run you through this.
Screwing in.
Get you to the example where it's actually running. So you notice there's no breadboards. Everything's just plugged directly in. This actual system doesn't require any soldering at all. There's the app. So you can scan and find your Bionic device. You can see it appearing right there in the app. Select it to make the connection, and then you can just control whatever pose you want. Just with the buttons. We got a hang 10 sign, thumbs up sign. And again, this worked for 2 years until a student got overly vigorous and ripped a cable. So currently it doesn't work, but we'll do some design changes to fix that up and get this whole thing working again. All the links for this exist. They're on the Dextrous Hand document that's floating around on the Bionics working group. So you can create this right now and you can build off of it. All these electronics do fit into an arm mold, so we can put this into an arm. So that's what we're doing with multi-motor Bionics. We're using these linear actuators. But what else do we need to do? How are we approaching simple Bionics? We're kind of using single, just individual motors. So you can see the, so this is the kinetic Bionic. We printed that up. We've got the motor embedded inside of the palm. This is directly from that designer. We've identified some changes that we would make to the design already. And this works with, I think I've got it set up so that it works with a potentiometer to open and close it. Right. So we just need to tension up the strings a little bit closer so that we can get it opening and closing. And all I'm doing is turning a little potentiometer dial to open and close this. So we do that to make it easy to test in the lab. And we're using that for testing grip strengths of these things. So we've got that for a single motor, and we're trying to figure out, okay, what kind of force does somebody actually need to do some of these daily tasks? How much pressure do my fingers have to actually exert on something to actually hold it? And we're trying to do that absent using any kind of friction, using just the actual force of the device, not trying to mimic skin yet, just trying to get an idea of how much force do we need, how much pinching force do we need for this to actually work. So that involves single servo Whippletree systems. I've seen some work and some publications of individual motor control using kind of kind of adaptive kind of mechanisms and mechanisms to do multiple adaptive grip poses with just one motor. So that's the paper that I'm referencing right here. And I did on my sabbatical a couple years ago, attach this motor to the gripper thumb. So that's freely available that anybody can use. That works with just a little button that you push, but we can implement that with the little force sensitive resistor too. So that's kind of our approach to single motor bionics. We're gonna start trying to get some numbers to test these things out. You can see this device, it actually worked pretty good. All the electronics just fit into a running armband to open up and close the hand. This was on a timer so that the finger would open, you'd position the hand where you wanted, and then it would close. But we can use the force sensitive resisting now to control this as well. All told, the price for all of this, all the plastic, all the screws, the motor, the electronics, the battery, the armband, I think it came out to $60 for that kind of device. Super cheap, super easy. Yeah. So that's what we're doing with the actual Bionics, with the designs. Now, how are we trying to test these? So testing, we're working on developing a testing rig. There is a survey that's out there. We're doing an IRB approved studies to trying to get some numbers out of what people want in a testing rig so that we can publish that. The testing rig we're working on, the big thing people want is how do we assess grip strength? So what I would tell people now is to use a blood pressure cuff. But what we're working on is something that we can use an Arduino to do that as well, so that we can get some more systematic data that's maybe a little easier for people to wrap their heads around. So the testing rig we've got kind of some sensors. So here's one version of it. We've got just a cylinder. So the cylinder designed to be the size of a 20-ounce bottle. Figuring that's a standard kind of size thing that people are trying to pick up. And inside of there's a strain gauge. So this strain gauge measures how much force you're applying to actually squeeze this. So when you squeeze something, it'll measure the force and it'll spit that out in an analog kind of unit. We've got an amplifier right here that amplifies that signal so that you can get a better range. And you can really detect very small changes in the force that you're using to grab these things. So what I found so far is this doesn't work great for e-NABLE hands, because e-NABLE hands, they can't grab it strong enough to actually get the force out. We can't get that in there, right? We can position them and it is squeezing it, right? You can position the thumb actually according to these two screws so that you really are applying the pressure where you need to apply it. You're squeezing it, but you're not getting out enough pressure from any of these devices to actually make a dent in this. So this is an avenue that we're going to keep pursuing. We are pursuing this with testing 3D printed tourniquets as well. It works great for that, not so great for this. So what we're doing there is we've moved back to my favorite thing. We've got the little force sensors. So these little guys, you can position these in the fingers and then you press it up against it, position it just over the thumb, start closing it, and it pushes against the thing you're holding. Put it on one side, put it on the other side, and you can get a measure of that force that you're pinching something with. And what you can do with these sensors is you can calibrate them. So you can take just standard masses. So because I run a physics lab, I've got standard mass sets. So just little, let me see if I got these. Go anything you'd find in a science lab, right? Take these, stick them on top of your force sensitive resistor, and you can get a calibration between the analog digital unit that the Arduino is giving and the actual mass. So from that mass, you can get out the force, so you know what kind of force you need to actually grab these things. So you can make your calibration right here. So you got your analog digital units versus the grams that actually equate to that. You can see it's not a straight line, it's kind of curved. So you can fit a polynomial to that. And you can get your calibration out so that you know then when you're actually using these to grab objects, using these force sensitive resistors, you actually know what force that's applying and you can get real world numbers out of that. So what we found, takes about 500 grams of force to hold a hard plastic bottle, a hard plastic drinking container. So we figure that out by actually taking two of these and we pinch this in between the fingers. And then we just gradually loosen up how hard you're holding it until it slips. Once it starts slipping, your force is out. So that's the force you need. That's the grip strength we need to get out. We need to get 500 grams of pinch force. So what we need now is a good system to say, what input force do you need to get that? So can your motor provide that? And we can calculate that. We can calculate that based on the torque rating of the motor. So motors, their ratings, you can see this is a 20 kilogram. They write 20 kilogram. That's not a torque. It's 20 kilograms times centimeters. So you need to kind of take whatever force you want out, and you can do the calculations based on where your torque is, where your force is being applied. So we have a little winch on this motor. You can just measure the distance from the center out to where your string's attached, maybe a centimeter. Use that to get out what torque you can get out of here. And then you can figure out, can I get the force that I need out of the motor that I'm using? You can use that to pick your motors and really pick the perfect motor that you need. We can optimize this kind of test, so we can use 3D printed objects, probably with just what's base mode. So we just get thin wall. So that is something that's squeezable, but we can get out whatever size we want. And we can standardize those sizes then, so that everybody gets the same exact object that they're testing. So we can test this systematically. We can send this off to schools. Schools can build this, and we can get a metric ton of data to actually use. And if we get enough data, even if it's not all gathered in the exact same way, if you have enough, you can do statistics. And then that's where you get out meaningful conclusions. So let's get some statistics. Let's get some data out in large amounts. Take advantage of all these students that want stuff to do. And then the other big piece that I think is missing that we could use is approaches to bionic testing. So if you want people to use a bionic device, they need to be able to use the control system. That's key. If they can't control the thing, then they're not going to use it. So you need to train them how to do it. And you need to make that training easy, and you need to make it fun so that they actually do it. People won't do stuff if it's not fun. So what we're starting to try to do is create game-based training using some Unity physics game engine. So do some computer programming, get your kids, get your students involved in this. Elementary schoolers can make things in Minecraft. They can make things in Roblox. They can make these kinds of games. We're putting it into VR just because the university invested a lot in it. So I need to find ways to justify that investment, but you could do it with 2D gaming. I would imagine you want to make a game that'll work with a cell phone, because everybody in the world has a cell phone. They might not have running water. People might not have running water, but what I read is they have cell phones. So make a simple cell phone graphic that works, plug your little sensor into your cell phone, set it up so that they can take their little flexible sensor, they can strap it to their arm with some Velcro, and they can use this as a game controller. And then you can use all of that data to create your control system so that they're trained on how to use these things, and they can get reliable results out of it. So I think there's a huge potential impact there. That's kind of largely unexplored. There are some groups that are doing this. I know Limitless Solutions in Florida is doing some video game kind of things with their bionic limbs, but they're using, again, myoelectrics, which I don't think I want to do with a large scale e-NABLE distributed kind of bionic device. Let's see where my time is at. So that's kind of what we're doing. That's our approach. We can show this little video. This is Catherine. We need to give her time in the spotlight. So she's wearing that Myo armband. Again, this is when we were using myoelectrics. And you can see on the screen, there's a virtual hand. So she has now graduated from Marymount, and she has a master's in biomedical engineering that she got from Virginia Commonwealth University. She's now working at Merck as a bioengineer. Maybe I can convince her to come back and keep working on this. But she did similar work to what Megan did. Megan was controlling the prosthetic actual hand. Catherine is controlling the virtual hand. So you see it's mimicking her movements. This was all built into that Thalmic Labs MyoBand. That thing was about $250, little too fiddly to use. I think there are newer ones that are coming out that are more open source. They might be worth looking into soon. Here, she'll start doing some poses in a second so you can see what kind of training things. She was very excited this day. She's like, I got it working. I have to come show you. There we go. So when she pinches her hands, fingers together, that open the hand. When she bends her hand in, that gives the peace sign. And this was a semester-long project for a student that's a senior, but had no computer programming experience. So your students, if you have students, can do this. Volunteers can do this. You can make fists. Very exciting. And then nice little fist bump and the virtual fist bump too. So that's the kind of work that we're doing in the lab right now. And I am happy to answer any questions that anybody might have.
That was a great presentation, Eric. Thank you.
Yeah. Thank you.
I noticed there
Eric, I
were
just-
a bunch
Other
of
thoughts?
questions.
Yeah. Questions, comments?
I saw a bunch showing up in the chat, so please go ahead, anyone.
I was just going to say, Eric, that I think your focus on what is practical, useful, etc., is perfect and in marked contrast to the usual engineering students' effort to drag in everything cool and new without sort of thinking about how is it actually going to make a contribution. I think the technology you're developing and the educational approaches and the just the general approach has got real promise. I think the age of open source bionics that are used may actually be upon us because of what you're doing.
I hope so. My goal is to get something that works well enough that I can use it in introductory classes, and students can learn engineering by building them, and then I can take it and I can send it somewhere. I know
Very cool.
students are building complicated ones. I know students are building non-complicated ones. They're building it all from scratch, which is great for them, but then nobody uses it. It just sits in a closet.
Exactly.
I want them to build it and send it somewhere. So,
Have you had any users, amputees, using any of your devices?
I haven't. Everybody I get, they have a palm, so they don't have the whole missing hand, so they don't need the Bionic. I know Lawrence, I think his daughter is using a Bionic that he designed, which is based on the kinetic hand, and I think they took the motor and moved it up top. So I think that's the next thing to look into, is how to create this that can accommodate the palm, but has the motors and circuitry kind of on a back end. The problem with that is it gets very bulky, because you have to have the batteries, you have to have the motor. You can only shrink that down so much. So that's tricky. So, but I'm working on it.
That's great. That's great. I embarrass myself half the time I ask this, but Lawrence, I don't know if we've met. If you want to introduce yourself, it's nice to have you here.
Thank you. Thank you very much for having me. Can you hear me?
Yeah.
Okay. Yeah, like Eric said, my daughter had an accident a year ago and she lost her fingers and thumbs. So that kind of made me interested in finding something for her. And when I was looking, I found a lot of the work that's connected to e-NABLE. And it was very interesting to me. And I actually felt like a wrist-actuated device would probably be the best, even more practical than the myoelectric. And so I've made a few. I made the kinetic hand, and I made the Phoenix hand, and I made the Flexi hand, and I may have made something else, but I can't remember at this time. I actually made. There's a hand on Thingiverse called the Dextrous Hand that's Dominic Scalisi made. I'm going to show it to you. It looks like
Now that's a sophisticated device for a
This.
newbie.
Can you see that? Yeah. And it's got buttons and it's kind of all kinds of interesting stuff. Which actually we feel like is a very interesting design. But the problem my daughter has is that, and I don't know what's going to happen over time, but the problem that she has is that her hand is sore. I think a lot of your devices are used by children and people who are born with a missing fingers or thumb or whatever. But I think this is true for a lot of people who have an amputation, have an accident, is that it's quite painful and it can last for a long time. And so I would say the most practical hand to her has been the kinetic hand. And I think it looks nice too, which is kind of has an appeal. But she gets sore, and so that's one of the reasons why I thought maybe we can find a way to use a sensor and put a motor on it.
You might consider the gripper hand as a non-motorized thing that does the gripping for your daughter. It's nowhere near as nice looking as the kinetic. And I don't know that anyone has done a kinetic gripper, which is something I think would be the right thing to do. That's the one that's got most of the fingers don't move. The thumb, however, is spring loaded. And so you can just sort of push it onto something and it will hold that bottle of soda. So that's something to look into, is the gripper, to see if the mechanical function might be helpful if she doesn't want to be actuating the thing herself. And if so, you've already demonstrated the sophistication. You might want to look into marrying the kinetic cosmetic with the gripper mechanic.
Yeah. Yeah, we're looking into all kinds of things. I mean, she does go to she plays the viola, and so on Thingiverse there was I think you may know about it, the viola thing. So we adapted that. It needs a little help because the angle isn't quite right. But she plays very well with it, and we're going to work on it a little bit more. It needs a little bit more adaptation.
How old is she?
She's 18. She'll be 19 soon.
Right.
So she's kind of a good test candidate for all of this, because she's young, she's strong, she's got a good mind, and and she's thinking about it. She's right with me. We're like it's things happen in life. It's difficult sometimes, but it's been wonderful to work on these things together.
That's so great. Where are you located?
We're in North Carolina, in a little town called Hiddenite, about an hour north of Charlotte.
And do you know the Helping Hands group with which Utkarsh represents today?
Oh, who represents it? Let me.
I represent the Helping Hand Project.
Oh, hi.
We have.
I am. Go on.
Hi. We have a couple chapters located in North Carolina.
Mhm.
I'm a student at NC State University, so that's the chapter that I've been most involved with, is located. But we also have a chapter in UNC Charlotte, which should be close.
Yeah.
I'm currently located in Cary, North Carolina, so that's by the triangle. So that's a little more central. But yeah, it's good to meet a fellow North Carolinian.
Yeah. I tried minimal contact at first. I think I reached out to a lot of people. I've reached out to Matt Botel, who made the kinetic hand. He's been very helpful. He's actually working on a motorized version of his kinetic hand. He showed me a photo of where he's joined the gauntlet with the hand, and he's extended it, and it looks like he's made a place for a motor. I've used the servo, but he's using a motor with a linear potentiometer to sense where the position is, which seems very interesting. I think a simple design could be very effective. I like what Dominic Scalisi has done with the buttons and the different grips. It actually works pretty well, and we're in quite a bit of contact with him. We actually visited him recently, and he's very interested in making something pretty good.
That's great. We should give our regards to Dominic.
Okay,
It was an incredibly impressive thing that he did, and I'm sure he's delighted that there's someone working on it. That's
yeah,
great.
he is. It's encouraged him. He was a little bit down, I think, but probably the complexity of the design was a little bit of a challenge for a lot of people. But anyway, so we're enjoying working with him.
Yeah, which brings us back to Eric, who seems to have learned the lessons about complexity of design and is really, I think, pointing the way. It's a hugely important issue for us, for our community in particular.
Yeah, I understand. And so anyway, you want to, I can show you, I mean, I did post a little video of my daughter using the hand, and a little video of the mechanism, which is very simple, but I think I can adapt it to be something useful. She was using it today to do some screen printing. We have a little print shop here, a 2D print shop. And we do screen printing. So she was using it to grab things and move things around. And that was kind of encouraging to think they could be useful. But
speaking for myself, I'd love to see that video, unless there are other questions more relevant to Eric's presentation.
yeah, I don't know how I would, it's on the e-NABLE website in the little, Eric was talking with me a lot. I don't know how it works exactly. I posted my new post, and then he responded, and I responded, and then I put up the little video of her using the hand.
Okay, I'll look on the hub.
Yeah. So I can show you, if you all can see, can you kind of see this thing? Oh,
Yes.
there you go.
Especially.
So it's a standard kinetic hand. It goes the opposite way that I move it, so I've got to get used to that. Then on the back, it's a little bit like I've forgotten his name, Para Michelle or something like that. But if you see here, you can't make it out because it's black, but I put a Whipple tree design that was from the maker of the Flexi hand, and then I used a little bit of flexible stuff here, if you can see it. And that was I think a good thing, because what it does is the servo doesn't really know when it's touching something, but the servo keeps going even after it's grabbed. But it has spring, it's sprung, so it actually is fairly functional. I'm quite happy with it, really. It's got potential, and I'd like to tidy up the design. You know, I have this M5 thing, which I don't know much about these Arduinos or anything, but I followed his design a little bit. I've simplified it. My daughter, when she used the pressure sensor, like the way it was done on Thingiverse was that when you, it was according to the pressure you exerted, was the servo responded. But that was kind of difficult because it wasn't very precise. It would jitter, and then, you know, she relaxed and it would open, and also it caused the same problem as using it wrist actuated. It was sore, and so I wanted to make it on and off, and so that's all I did. I took the code and made it super simple, and now it's on and off. So now oh golly, okay, so now I press in here, and I put it in here, and I press, and I press, and I press, and I press, and it opens. Sometimes it opens. Usually it opens. There you go. Anyway, so what was I going to say? There was something else that I think is significant. Oh, also the armband. We did the armband that's in that design on Thingiverse, and that wasn't very. It didn't seem to help her. When she really doesn't have the musculature that she used to in her arm. So I think that's something to consider with the FSR, is that the recipient might not have the it might not have the strength. So we put it in the palm, and she has good strength there, but she can't, you know, she doesn't want to be exerting that pressure all the time she's holding. So we made the on-off, but I'm not totally happy with the on-off in the sense that when you're approaching an object to pick it up, what would be more normal is that you'd close your fingers incrementally until you get them close to the object, then you position them more precisely, and then you grab the object. And she's not able to do that because it's on and off. You know, she gets it close, she thinks it's at the right point, and then it closes, and that's more a problem with small objects. But if we could make go on.
I was just going to say one idea that we thought about is you put a sensor on the outside of the palm here, so that when you make contact with the object, that's when the hand decides to grip. So it's actually just controlled.
With bigger objects like that, it's not so much a problem. It's kind of picking up little things, which she can pick up. Like she can pick up a, you know, I don't know, a key or a bottle cap or something. She can do those things, but that's awkward. That's where she gets close and the hand closes quick and it's a miss, you know. But if she could, what I wish we could figure out, and maybe someone can help me, is that the FSR is proportional as she applies pressure, so that the fingers close gradually, and then they come to a point where she could send another signal or maybe exert a lot of pressure or something, and it will lock. And then she doesn't have to exert any pressure, and it's gripping. And then there would be another signal, maybe another FSR, and to release. I think that would make it a lot more functional.
Sounds doable and interesting. Doable not by me, and interesting to all of us.
Anyway, so that's where we're at. That's what we've been doing.
That's a great story. Tell your daughter that if she is in fact interested in being a tester, I suspect there are a number of people who would like her perspective on their various devices.
Yeah, we would be happy. We're interested in just finding. My perspective as her father is just to find her the best I can. We don't have the economy to, afford the best the world has to offer, but maybe the best the world has to offer isn't the best anyway. We like we like this whole realm. We like the idea of collaborating and working together and things being a little bit lower technology in a way, like more available for everybody.
Yeah.
Lawrence, can I just say something? I'm Alberto from Bolivia. First of all, we are the peace. I'm here because I had the same experience with my daughter. She lost her hand in an incident when she was 2 years old, and so let's talk. For sure, we can try to help, even because I've seen Eric work with the pressure sensors and also I think you have shown the kinetic with the M5. We are working. We are trying to do more or less the same. The project with the pressure sensor and the M5 was done by Michele, of our volunteer, and I worked on it a few months ago, trying to make a new version with some improvements, starting exactly from the point you mentioned. The pressure sensor was not usable in a real case because of its way to activate the end. And in general, I think we can work together and share our experience, trying to figure out what can be done for our daughters and for our children in general, and for who need this kind of stuff. At present time, my idea, I agree 100% with what said Eric. There is the need to simplify on side and to have some basic that can be really used by someone, and maybe we need also to start the person that we know that can make some experience and start to try the devices to give feedback and try to make sounds that can be then widely used by people. We also have some people with limb amputation that is waiting for those devices, but even if we are working from a lot of time, at present time we are not ready to give to them because they are really usable. But it might require some time, but it's something we must try to achieve, I think, because it's something that goes beyond the need to manage the technology and to just find the solution. You know, by your experience, I mean, you have your daughter, I have mine, and we must do something to help them. This is just to help anyone that has this kind of needs, because the technology available is enough to create something. We just need to join our efforts. Or so today I'm leaving the meeting really happy because I've seen that from one contributor, one volunteer, some other way of it, and I think this is the way. This is the right path.
Oh, that's great. Alberto, you're in Spain?
I'm in Italy.
Oh, in Italy, I beg your pardon. Okay, great.
Yes.
Well, I'm very happy with what's gone here. Ben has excused himself. So Vivek, I'm going to hand the moderatorship to you and let you make any announcements or say goodbye to everybody.
Well, thanks, John. It was fabulous. This was one of our best meetings. Thanks, Eric. Thanks for doing the pitch, and we'll keep in touch and see how your work is going. It's fantastic. Maybe for the next meeting, Alberto, you have a bunch of stuff you're doing with the electronics for the hand. Maybe you could share it at the next meeting in September, if you don't mind. I can talk to you.
We can work on that definitely, and even for what said Eric about testing devices, we can maybe start a discussion, because we can I think we can help also on this, but as always, we are available on this kind of stuff with all our group of volunteers.
So one last request, Eric, would you mind sharing your presentation? I know it's the videos there, but the PowerPoint page, is that something you can share?
He already shared it in the chat, and I included it in your comment. That was a really great idea to include that, Vivek.
Great. Okay. Well, I think we can wrap up here, right, Ben? How do I end this without screwing everything up? Do I just hit end?
Just hit end, and the recording is automatically included.
Okay. Okay.
Thanks everybody, and if we want to follow up in the hub, we can continue the collaboration.
See you in the hub.
Thanks.